please welcome Brian.
Thank you. So a couple housekeeping things from me here too. One, I had no idea this is going to be recorded, so I have to change my entire pitch right now. Second thing is I am Brian Venturo. I'm no longer the CTO of CoreWeave. As of last Tuesday, I'm now the Chief Strategy Officer. Somebody finally figured me out. When I talk about, the Chief Strategy Officer role is kind of interesting for somebody that's running data centers. I think that historically, well, actually first, how many of you operate in the data center industry okay, great. If you have more than 5 megawatts of capacity, come see me after the talk. Chief Strategy Officer title for Brian. It's interesting role for me to be in, but it shows how strategic we believe our data center capacity to actually be to our business, right? Not having data center capacity would be existential as a threat to CoreWeave. Right, so I spend almost all of my time across 3 parts of the organization. It's data center construction and delivery, it is capacity planning, and it is product. Today, I'm going to talk to you about what that means inside of CoreWeave, how it's changed over the past several years, and the craziness that has kind of ensued over the past 18 months. Let's see if I can not screw this up. State of existing data centers. This is what you would have walked into, let's call it 5 years ago. It may have been an enterprise data center that was built by a bank. They may have spent $20 million a megawatt. It was built to an infrastructure. It was built for workloads that can never go down. They were balancing cost and performance across the facility. It was a lot of CPU compute. There was some storage, but everything was pretty disaggregated in the way that it worked together. Right, this is that idea of fragmented usage. So fragmented usage means if you have 1 million services inside of a data center, that if one goes down, your 999,999 others aren't impacted. And the last piece is energy lean operations. They were building for supporting, let's call it 5, 7, 10 kW per cabinet, but they never actually consume it. This is a chart here that just shows power density over the years and what data centers are capable of doing. On the high end here is over 50 kW. I think that category is actually going to change over the next 12 months here. Jensen spoke yesterday about GB200 and some of the power densities required to be able to run these things. We're looking at over 120 kW per cabinet now. This idea of transitioning legacy data centers, and we have 2 different strategies at CoreWeave. One of them is the tactical strategy, where we're trying to solve for data center capacity in the next, let's call it 6 to 14 months. And 6 to 14 months means that we have to go find buildings, right? Whether that's from, it's from providers in this room, or if it's for brownfield retrofits, or if it's, powered shell in the middle of nowhere, we have to go find and build that capacity to be able to meet these client demands, right? And it's not something we can get off the shelf. And since we are strategic campus planning that's been in place for years. So, now we're in this retrofit kind of part of our strategy where we have to go in and say, okay, how do we take this thing that was built for a bank and make it run one of the most concentrated type workloads possible in like 3 months? Right, so, this pretty much involves ripping everything in the data center out. It's not just servers, it's not just switches, it's not just cabling, it's also some of the MEP. It's reconfiguration of the power trains. It's taking a completely fresh look at this existing infrastructure to see how can I use this for my clients. So what does a retrofit look like? This is one of the few pictures I put in here, and I feel like half the people in this room would sue me for NDA breach if I did more. But this is from one of our campuses where we walked in, and I'm sure some of you have been on the other end of those phone calls. I apologize. But our clients are incredibly demanding for what they need and when they need it. And it is, like I said, data center capacity is existential to me. Access to this GPU compute is existential to them. When we're designing these data centers, how is it designed differently, right? And there's 2 pieces here that are really important. The first is that it's designed for a singular use, right? And it's not saying, oh, you're going to run this one type of workload. You're going to run one workload. Right? You have a cluster of 25,000 or 30,000 GPUs that are all working together in concert for one job. One GPU fails, or one server fails, or one PDU fails, the entire job is going to stop. They have to load from checkpoint. It's going to be hundreds of thousands of dollars for them to recover from this. So it's incredibly important we're designing the data center and our infrastructure and software stack to be resilient around that. The other piece here is pushing the energy limit, right? This is something that we've run into a few times now, where the data center operators and the operations team on the ground didn't understand that these workloads, they pulse, right? And pulsing here doesn't mean you're going to go from 5 kW to 7 kW. It means you're going to go from 1 megawatt to 20 megawatts in a period of 5 seconds, right? And when you have that type of power change hit the local grid, you basically create grid brownouts, right? And it's so critical to us that we have really good UPS systems that are backing our power, because we can deal with the voltage sags that are created from that effective brownout, but the grid around us is screwed, right? So we have to work with, like, how much of this can you actually handle? How do you think about power sags? Like, what can we do here? So they're comfortable and understand what's going to be coming and how they ramp up plants and how they serve that area of the grid. So these aren't use cases, or these aren't pieces of the use cases that the industry is designed for the past 20 years. With that increased density, with the power being on or off, and with the scale of the power, it's creating challenges for these local utility providers. So I'm typically not allowed to do this, but I took out all the numbers and things. So if you count the bubbles, that's good for you. But this is the map of our current data center footprint across the world. I'll give you some figures, and then I'll get yelled at later. We either contracted power or power rights. We have over 1,000 megawatts in our portfolio. We have single campuses that are more than 300 to 400 megawatts. When I said that data center capacity is strategic to CoreWeave, I truly mean it. Right? Is if we don't have the power, we don't have the infrastructure to deploy, new clusters, new GPUs, new infrastructure for our clients, we might as well stop operating, right? And I think this is a critical piece that a lot of folks outside of this hyperscaler community really, really respect. We've started making inroads into Europe, but a lot of this is really around this idea of, okay, a lot of this capacity is retrofits. A lot of this capacity is, okay, take this thing and make it work for our use case. But going forward is the second part of our strategy here, which is, okay, how do I design those huge campuses to house 500,000 GPUs or 1 million GPUs for a single customer, right? And I mentioned before that we have rights and we have campus power that's a little bit further out. This is what one of those is going to look like, right? And this is on a campus in Richmond, Virginia. This is a place where we're going to be hundreds of megawatts in many buildings that look like this. But what does this new data center look like? So, we're never going to get away from air cooling, right? So there's some component of our data centers that have to be air cooled. So there's going to be what I would consider traditional cooling infrastructure inside the facility. But the majority of everything that we're doing now, starting around July of this year, is going to be liquid cooled. And it's direct-to-chip liquid cooling, and the densities have gotten insane. Right? And we're not just designing for what's coming from NVIDIA now, but we're designing for what's coming down the road. And how do we future-proof this? And how do we think about containing that heat? How do we think about getting the heat out? How do we think about delivering enough water? How do we think about the different fluidic systems? I can say this, that there's one group in this room right now that's working with us on a design to do 100 kW of air and 300 kW of liquid in the same cabinet. Right, so the boundaries that we have to push here have gotten incredibly aggressive, and we have to do it. Right? It's no longer, oh, we could invest in this in 3 years from now. We have to do it. We just deployed what I thought was going to be the next generation of our cooling infrastructure in a data center facility, and before it even gets turned on, it's obsolete. Right, and we're making these big, almost lab-style bets in 20 to 30 megawatt chunks to try to understand what works. And it's not necessarily like the idea to iterate on it. It's, okay, we're moving from this design to this design to this design over a 6 months period of time, right? So when you look at this campus here, what these buildings, let's call it, from a conceptual perspective, these buildings may be 70 megawatts apiece, right? They'll have a 10 megawatt data hall that's purely air cooled, and the balance of it will be liquid cooled direct to chip, supporting densities, over 120 to 200 kW per cabinet. So this is going to bring a lot of challenges. The operational team inside of CoreWeave that's responsible for this, he's sitting right there. Raise your hand, Jacob. Sucks to be you. Question of if we're able to operationalize this piece of our business, we have to operationalize this piece of our business, right? And I'm going to talk a little bit about software and what that means in a minute. So I've kind of mentioned a lot of this stuff here so far. Redesigning the data center from a power perspective. We're not really building anything with 2N redundancy. It's all N+1 distributed redundant. We internally to CoreWeave, we like the distributed redundant piece because we're able to, in the event that we have bursts, we're able to handle them. We've been in situations before where block redundancy has caused us some issues. It is on the rack level side, it's okay, how do I actually get that many cables and that many fiber cables, that many power cables? How do I do all the cable management in there? It's designing, designing infrastructure around the cabinets to be able to do that. But this is inside the data center has now become this complex optimization problem. Historically, it's okay, you have a couple fibers that run to a cabinet, it's no big deal. But now we have hundreds of thousands of fibers inside of a single facility. And how do you route them? How do you stack them? How do you replace them? How do you manage them? How do you tag them? All of these things are actually complex optimization problems. So the cooling piece here, over the last 3 generations, NVIDIA has stepped up from 300 to 400 to 700 watts, and will now be going to 1,000 watts on B200 and higher on GB200, right? Is how do you cool that? Air cooling can do so much. What we've found is that when we have cabinets that are too dense from an air cooling perspective, that we actually create too much back pressure inside the hot aisles, right? And we have hot air that leaks out through the front into the cold aisles. And it's just, in theory, you can do these things, right? It's just that in practice, if you're not running 100% of your workloads all at the same time, you're going to have weird environmental problems that happen inside the containment zones. The way that we've dealt with this from a retrofit perspective is we've spread things out, right? I'm typically never going to be real estate limited, but I'm always going to be power limited, right? So if I decrease the density of the cabinet, it's easier for us and the provider to handle it. We don't have to worry about hotspots as much inside the hot aisles, like I mentioned before, but leaking out in the cold aisles. But the other way that we deal with this today in true CoreWeave fashion is through pure brute force, right? And brute force is, if I walk into a facility and we're worried about the cooling infrastructure, run it at max, right? It's too important for these workloads to not fail, that we have to try to solve the problems through the brute force if there are problems, right? And we'll redesign it later, we'll re-engineer, we'll go for efficiency later, but first thing to do is get the environment stable, solve it with brute force. So, as we move in these higher densities, the air cooling option is no longer on the table. I thought we were going to have a little bit more time for that, but here we are. So, now we're going back to cooling. Like I said before, Jacob's life is terrible. He has to do it in about 3 months. We have our first scale deployment of that going live in June, also with somebody in this room. And then pretty much everything that we're going to be getting delivered after July is going to be liquid cooling primarily. So the piece here in the networking, and we have a number of clients that I think were reasonably untethered to the physical reality of actually building these installations and what goes into it and how you do it. And the picture that I have here, this is just of one of the InfiniBand SuperPod spines in one of our facilities. It's a 32,000 GPU facility. The SuperPods are 4,000 GPUs wide. But there's 3 or 4 levels of ladder rack here that's 24 inches deep that has thousands and thousands of cables on it, right? And how do you route this back to your InfiniBand core? How do you route this back to your main networking rooms? These are all that we face in the field, right, that you kind of just have to solve problems for. So, each of these installations has hundreds of miles of fiber, right? And we pull the fiber in, let's call it 3 weeks from start to finish, for these 16 to 32,000 GPU installations, right? So, we have to go in there, we have to have a great plan, we have to go very, very quickly, but this is a problem that we have to solve, right? And, from a design perspective, how do we think about, trunking those cables down the road? How do we think about, better modular delivery of them inside the data center? I don't have answers to this stuff yet, but this is stuff that we're thinking through. The one piece here that is critically important and I think is glossed over tremendously on operating this infrastructure is the software stack to do it, right? And there's people out there that say, I can go build this, I can go take GPUs, I can plug them in, I can give you internet. It's not that simple, right? These are incredibly complex systems with hundreds of thousands of single points of failure for a single job. Incredibly sophisticated provisioning and automation software. You have to have incredibly sophisticated health checking, both passive and active, to make sure, okay, is the environment operating to the level I expect it to? Is something breaking? Are we seeing any predictive failures? Being able to run those tests across the entire cluster to solve problems. The software stack here is what allows our customers to be effective and to push training workloads. Thank you, Gabby, for the time thing. To push training workloads to the limits, right? So the software stack of this should not be underestimated. It's why we have hundreds of engineers that are working direct with our clients to do this, right? So the data center historically, I think, has been a pretty unsexy piece of the conversation. I think that software and data center now are totally intermingled, right? And you can't run one without the other. On top of that, we have intelligent workload orchestration, scheduling, topology awareness to make sure that customers are scheduling their workloads inside the same pieces of the network if they want to minimize latency. It's understanding, visibility on different links, visibility on InfiniBand health. Like I said, these are crazy complex systems, and you have to have awesome automation around it. So that's kind of all I have on the data center piece. I'm happy to answer any questions you may have. Like I said, if you have more than 5 megawatts of capacity, I will talk to you. Anything I can do to answer, or any questions I can answer. Hi.
Oh, sorry. I'm going to give him the mic. I'm passing the mic around.
You're burning my time here, Gabby.
I know. I'm running.
Very fast question. Jose Castro from Pandiot. Regarding the infrastructure, the fiber, you're talking about single mode, multi-mode, because the clusters are very small sometimes. Any preference? And also, when you deploy from switch to switch, there is a fabric there. There's a complex connection, spine leaf, or typical.
So do we prefer single mode or multi-mode? We're reasonably indifferent on single mode versus multi-mode inside the InfiniBand fabric as long as we minimize cable distances, right? So we're always trying to minimize distance just from a latency perspective. Not saying that it causes problems, but we'd rather not have the problem available. How do we deal with switch-to-switch connections? Can you expand on the question a little bit more? What do you mean?
Usually when you have NVIDIA switches level 1 to level 2, they have to connect among each other, like one switch have to connect to all of them.
Yeah.
So that becomes very complex. Where do you do that? How do you deal with that?
Sure. So all of our InfiniBand fabrics are what are called fat tree non-blocking rail optimized, right? So it's it's effectively there's one connection for every GPU, every step of the fabric. Each GPU, so rail 1 is GPU 1 in a system, will talk to every other GPU 1, and if they ever need to communicate to GPU 2, GPU 3, GPU 4, all of that traffic is switched core level, right? So inside those spines, you'll have 2,000, 4,000, 8,000 GPUs that are able to communicate without going to the core level, at least in the same rail group. But how do we do that? It is I have an amazing InfiniBand team. That they seem to get a lot of work done. They have a lot of automation, and they never complain. So that they get it done, not me.
Thank you.
Following on that question too, with the 50-meter kind of distance limitation on InfiniBand, are you guys able to push the boundaries of that?
It's 50 meters with 2 patch panels
Gotcha.
in the middle. I'm not going to tell you what that really means.
Cool. And then the other question was immersion cooling. I know Microsoft, Google, NVIDIA are all going down the path of direct-to-chip. Do you see a future with immersion? What's CoreWeave's perspective?
So my take on this is that liquid cooling route to market right now, we have a clear path. We have environments that are set up and running. The immersion cooling thing, while interesting, to be perfectly honest with you, I don't know a lot about it, right? It scares me a little bit in that I don't feel like it's been done at scale yet. I know Google has operationalized liquid cooling at scale. So they're a bit of they've planted the flag in something that we know works. Not to say that we won't do it down the road, but at this moment, I think we've got our hands full on the liquid side.
So are you, without the liquid cooling component, are you good with what's your KW per cabinet, 45 KW?
No, so we have stuff that's done up to the 50 to 80 kW per cabinet in air-cooled environments, but they're specialized environments. If I had my choice and I'm not real estate constrained, I would put everything at 17.2, just so I know there's not a problem, right? We're walking into some of these environments, let's call it 10 megawatts of 2N and deploying, 17 megawatts or whatever it is, and we don't know how things are going to respond, and I know that if it's 17.2, I can handle it, right? We can always handle it with brute force. I'm sorry? We are. So I have an awesome backbone team, and they came to me and they spent a bunch of money. And the only guideline I had for them was I don't ever want to have a backbone outage. So they came back and said I need to spend more money. But we are using dark fiber wherever we can. And it's typically, we have what we call super pops internally that are, let's call it an Equinix or DRT carrier hotels. So like we're in NY6 up in Secaucus, we're in DC2 down in Ashburn, and we'll do dark fiber back to our data centers from there. And we have our own DWDM gear to light it up. We're actually just providing some of those metro services to some of our customers as well. But that's for everything from whether it's transport between our data centers to public internet to direct connects with big customers. It was a natural step for us. And over the past year, we've been investing in building that, and it went live about 2 months ago. We just don't really talk about it yet.
Yeah, I was just wondering, after you mentioned reach, what's your biggest cluster? What do you do when you exceed 50 meters? How do you architect when you have a large cluster?
So I'm looking at my CEO. He just smiled at me. He told me before not to go too crazy. Our biggest cluster today is 32,000 GPUs. The way that we deal with the InfiniBand length ratings is we will go to single mode if we have to, above 50 meters, or whatever the qualified length is for that facility. A lot of it is really around these two, is how do I optimize for this? There's a lot of conversations that happen in a pre-build phase of like, okay, how are we actually going to do this piece and how do we think through it? And for some of the site selection, it comes into play as well. It does not go across buildings today. Hi, Russell.
Have you had, so when you get up over 100 megawatts and you connect to the power grid, curtailment's coming into play. Have you had those kind of questions around how you can curtail workloads using storage?
We can't curtail workloads. Not at all. Right. Buy more generators.
I think that's the answer.
Yeah.
What's your smallest data hall contiguous space that you accept? What's your ideal on the high end?
My ideal is 100 megawatts in a single building. So I think like where we grow over 10 or 15 megawatts of critical IT, we'd be interested in something that's like 5 megawatts to start. It takes us like 4 to 5 megawatts to stand up critical services from control plane compute to storage to network, et cetera. So when we get into workloads beyond that is really where we need the extra power from the 5 to 15. We're just from a time perspective, the bigger the better for us, is we can only do so many a year, right? And while I tell them they can do 3 times as much, they tell me I'm wrong. So we just have to keep them as big as we can.
Okay, that is all we have time for. Thank you again, Brian, for presenting, and enjoy the rest of your GTC.
Thank you.